Hi, I'm Braden. I'm a grad student at Boston College, and I'm going to tell you about fixed points of pseudo-Nosov maps and knot-Floer homology. Everything I'm going to say today, by the way, is joint work with Ethan Farber and Luya Wang. So the first thing I'll tell you about is knot-Floer homology. This is some functor which takes in a knot in S3 and spits out some bigraded vector space over the rational numbers. Don't worry too much about what that means. You can just think about it as some algebraic object associated to your knot. So this functor satisfies a couple nice properties. It detects the genus of the knot that you put in. It tells you whether or not it's fibred, and it tells you about the Alexander polynomial of your knot. These properties are all of the form, the algebra of your knot-Floer homology telling you things about the geometry of your knot, which leads us to the type of question we're interested in today, called a detection question. If two knots have the same knot-Floer homology, are they equal? This is asking, what about the geometry of a particular knot can you tell about from the algebra of the particular knot-Floer homology of it? So what's known in this realm? Well, we know that knot-Floer homology detects the unknot, meaning that any knot with the same knot-Floer homology as the unknot must be the unknot. And that's just because knot-Floer homology tells you about the genus, and the unknot's the only knot of genus 0. It also tells you about the trefoils in the figure 8 knot, because those are the only genus 1 fibred knots. And to date, those are the only knots of a single component that knot-Floer homology is known to detect. We do know, however, that it detects some small links of 2 components, like the unlink and the Hoff link, and some small torus knots. So we did genus 0 knots, we did genus 1 fibred knots. What's the next place to look? Well, maybe genus 2 fibred knots will work. And the simplest one of those maybe is the 2,5 torus knot. So it's been a big open question for a little bit now, whether or not Floer homology detects the 2,5 torus knot. And the theorem that we prove is that, yes, in fact, it does. So how do we do this? Well, first of all, Baldwin, Hu, and Civic reduced this detection problem to purely a dynamics problem, a problem about counting fixed points of pseudo-Nosov maps. If you could show that any pseudo-Nosov map on the genus 2 surface with one boundary component has an interior fixed point, then this would imply the detection result. But the issue is that this turns out to be false. We actually found an infinite family of examples of pseudo-Nosov maps on this surface which have no interior fixed points, and many of them look like potential counterexamples to the detection result. The issue ends up being really just that they're not knots in S3. So if you start to do some analysis of a bunch of special cases for things that could potentially be in S3, then you get out exactly the fixed point result that you need. Any genus 2 fibred hyperbolic knot in S3 with some extra condition about the dynamics of the pseudo-Nosov map underlying it has an interior fixed point. How do we prove that fixed point count result now? Well, we use something called train tracks. And you can think about a train track as just some combinatorial representative of your pseudo-Nosov. In particular, it's some smoothly embedded graph in a surface. On the left here, I've drawn an example on the disk with 5 punctures. And why we've done the disk with 5 punctures for this example will become clear on the next slide, but just trust me for now. So what you can do with this graph is you can apply your pseudo-Nosov to it, and it will bend it and stretch it and twist it around, like in this middle picture here. But you can notice that it will stretch it around in a way such that there's lots of parallel strands. Like on the right here, I've kind of highlighted in yellow a little region around the yellow strand in your original train track, and you can see lots of parallel green and orange strands passing through it. And you can collapse down these strands that pass through it back to your original train track to get a graph map. So for example, the graph map takes in the orange strand and it runs through the yellow region once forwards, then the yellow region once backwards, and then the red region after that you can see highlighted on that picture as well. This is called a train track map, and our goal is to use these train track maps to count fixed points of the underlying pseudo-Nosov. Train track maps are pretty good at counting fixed points, but the issue is that there's a lot of them to look at. So the problem becomes a really big combinatorial mess unless you're careful. So we need a couple tricks. The first trick that we need is it turns out that if you have any map on the genus 2 surface with one boundary component, which is fixed point free, then it has to commute with the hyperelliptic involution. In particular, you can quotient by that involution and get out some map on the disk with 5 punctures. But a map on the disk with 5 punctures is just a 5 braid. And because the map you started with was pseudo-Nosov, then your 5 braid should be pseudo-Nosov too. And because the map that you started with is the monogamy of some fibration of some knot in S3, then the closure of your 5 braid as a knot should be the unknot in S3. So great, you have some 5 braid which is pseudo-Nosov and closes up to the unknot, and you can start looking at train track maps for that. These train track maps live on the disk with 5 punctures, and you can do a bunch of the combinatorics there because it's easier to work on the disk than it is to work on the surface of genus 2. So you do all of your combinatorics on the disk with 5 punctures, and then you can just simply lift Your train track maps back up to the surface upstairs and count fixed points there, and see what it tells you about the combinatorics of the train track map on the disk. And you can play that off of each other and see that there's really only so much that you could do to avoid having fixed points, and then you can finally just check the braids that those correspond to, and none of them end up being unknots. Thanks.